Thank you. So the focus of this talk will be the dynamics of a binary system in the highly relativistic regime, in the limit that one of the bodies is much more massive than the other. For generic orbits, there is a qualitatively new feature in the relativistic regime, and that is due to the transient resonances. I'll describe the properties and the effects of the resonances and the implications for gravitational wave observations. I'll also give some numerical estimates of the net size of the resonance corrections. The two-body problem in general relativity is, just a second, I wanted to minimize this screen. I guess it doesn't work. Oh well. In general relativity, the two-body problem is a significant theoretical challenge because it requires you to compute the dynamical space-time describing the binary. So two objects initially in a bound orbit will gradually spiral together as they emit gravitational waves until their orbit becomes unstable, the objects coalesce, and the final body brings down its perturbations and settles down. The regimes in the parameter space for the binary can be roughly divided into three main regimes in terms of the orbital separation and the mass ratio. So I've tried to illustrate this here, where I show the orbital separation on the y-axis and the mass ratio on the x-axis. For binaries at small separation, when the masses are comparable, one must use full numerical relativity. There has been much recent progress, but it is still very difficult and computationally expensive to simulate binaries with larger orbital separation or smaller mass ratios. But then one can instead use analytical approximation methods that rely on identifying a small parameter to be used for a perturbation expansion. So the main theoretical tools that have been used are post-Newtonian theory, which describe binaries at large orbital separation and where one can expand in the gravitational interaction potential. Post-Newtonian theory is very successful for describing systems like the binary pulsars, but it breaks down in the strong field limit. For relativistic binaries, in the limit where one of the members is much more massive than the other, so in this quadrant, one can exploit the fact that the mass ratio is now a small parameter and use black hole perturbation theory and two timescale expansions. So this is the regime that will be relevant for the rest of this talk. The small mass ratio highly relativistic regime also has direct astrophysical relevance because there's observational evidence for the existence of supermassive, meaning millions to billions solar mass black holes in the centers of many galaxies. So for the central arcsecond of the Milky Way, astronomers have monitored several stars, shown here, in the central arcsecond, and inferred that they were captured onto tight elliptical orbits around a central supermassive object. Even closer to the center than these stars, where the gravitational field is stronger, gravitational radiation will become important and cause the gradual inspiral of the objects into the central supermassive black hole. Main sequence stars will eventually get tidally disrupted and only compact objects survive. And the gravitational waves emitted from these compact object inspirals are a key source for future gravitational wave detectors. So in fact, LISA and LIGO can both see small mass ratio inspirals, but each of them is sensitive to a different class of sources. LISA will see the inspirals of compact objects into the supermassive black holes in the centers of galaxies, where the mass scales are the compact object mass of order mu 1 to 10 solar masses, and the large mass I'll denote by m. Due to the small mass ratio, the system will spend a long time, the last year or so, inside LISA's sensitive frequency band and emit an enormous number of cycles of waveform. So it will be good to remember for the rest of this talk that the number of cycles of waveform scales as the inverse of the mass ratio m over mu. The acronym for these inspirals is EMRIS, and the event rate is estimated to be about 50 to 100 per year based on simulations of the stellar dynamics in central cusps of galaxies. So LIGO could also see small mass ratio inspirals, but in this case that would be inspirals into intermediate mass black holes in the centers of globular clusters. The existence of such intermediate mass black holes has not yet been observationally confirmed, but there is some indirect evidence, for example, from ultraluminous X-ray sources. These systems would be intermediate mass ratio inspirals, or IMRIs, and the event rate for advanced LIGO is rather uncertain. So if such black holes exist, then maybe the rate could be of order 3 to 30 per year. Now LISA could also see intermediate mass ratio inspirals, but in that case it would be intermediate mass black holes going into a supermassive companion. The signal will be very rich in information, and due to the large number of cycles, one can do high precision studies. A key science goal is to test general relativity in the strong field regime where it has not been tested before. And the idea is to map the space-time geometry of the central object in a fashion that is analogous to what geodesy climate satellites do for mapping the Earth. Because in principle, the gravitational waves encode the values of all the multipole moments of the space-time. So one can measure the quadrupole to very high accuracy and use that to test for the no-hair property, that for a black hole, all the multipole moments are uniquely determined in terms of just the first two, the mass and the spin. Then there's also much astrophysical information contained in the signal. For example, by measuring the massive object's spin, one can get some information on its growth history, for example, merger versus accretion. The inspiraling object's masses will give some information about the stellar populations in the centers of galaxies, and the distribution of orbital parameters such as the eccentricities can give some information about the formation history. There's also some potential to do cosmology with LISA. One could measure the Hubble constant to about 1%, provided that one has an independent way of determining the redshift to the source. So one can either do a statistical analysis of an error box on the sky to identify the redshift of the host galaxy, or if there's an electromagnetic counterpart, that would also be helpful. But detecting such signals and extracting all of the signs from the measured data stream will require accurate theoretical models of the waveform as templates for matched filtering. The accuracy requirement on the template is roughly that it must remain phase coherent with the true signal to about 1 cycle out of the many, many cycles of the inspiral. So that would be 1 cycle out of about 10 to the 5 for LISA measurement templates. And for detection templates, the accuracy requirements are less stringent because maybe shorter segments of the signal will be used. And what is required are waveforms for fully generic orbits. They have to be eccentric and inclined orbits around rapidly spinning black holes. And you can see here in this figure I illustrated the waveform from just a geodesic. So the waveform is shown here, one of the polarization components versus a retarded time. And you can just see qualitatively it looks fairly complicated. So there has been a great research effort aimed at providing such accurate templates. And the foundation for all of these approaches is the fact that the mass ratio, mu over m, which I'll denote by epsilon for the rest of this talk, is a small parameter, so one can use a perturbative treatment. There are 3 main timescales in this system. On short timescales, the orbital time of order m, which is of order seconds to minutes for typical inspirals, the small mass mu will move on the geodesic of the background space-time. On longer timescales, the radiation reaction timescale, which is of order m over epsilon, which is of order months to years for inspirals, gravitational radiation reaction will cause the orbits to gradually evolve. And then there is a third timescale, which is the timescale for geodesic orbits and true orbits to dephase by one cycle. And this is the dephasing time, which scales as m over the square root of epsilon, which is of order hours to days. So this dephasing time scale tells you after what time you can no longer approximate the motion as being a geodesic. So, but you can qualitatively think of an inspiral as a flow through a sequence of geodesics. So locally in time, the motion will have the main features of bound geodesics incur. So for bound orbits, generically, they're confined to a toroidal region around the black hole, between a minimum and a maximum radius and a maximum inclination from the orbital plane. So the motion fills out this entire region here, and then you have to imagine it rotated around the spin axis. The shape of this region is characterized by the constants of motion energy E, axial momentum Lz, and a Carter constant Q. And in general, there's a different frequency associated with the radial motion, with the polar motion, and then there's an additional rotational azimuthal frequency. You can see here in this plot where I show the frequencies versus the size of the orbit that at small orbital size, close to the black hole, there are three distinct frequencies which, as you go to larger orbital separation, so closer to the Newtonian limit, they all coincide to form a single frequency orbit. And you might be familiar with the beatings between the frequencies. They give you the precessions and frame dragging. For modeling inspirals, it is convenient to exploit the fact that geodesic motion in Kerr is an integrable Hamiltonian system, so one can define generalizations of action angle variables. So we'll use, for the action type variables J, we'll use E, L, Z, and Q with the rest mass scaled out. And then there are four angular variables, QT, QR, Q theta, and Q phi. This set of variables is convenient because it is adapted to the phase-based geometry of the system, which is foliated by invariant level sets of the first integrals, with the three spatial level sets compact and diffeomorphic to a torus. But because the background has an azimuthal symmetry, the tori in phase space are effectively two-dimensional, and the motions are characterized by the fundamental frequencies omega r and omega theta. In general, these frequencies will be incommensurate, so meaning their ratio is an irrational number, and those orbits will be ergodic and fill out the entire surface of the torus after a sufficiently long time. The geodesic motion in the background is corrected by self-force effects, which describe the small object's interaction with its own space-time distortion. So the self-force is analogous to the Abraham-Lorentz-Dirac force in electromagnetism. The gravitational self-force will cause the frequencies to slowly evolve, and that can lead to the occurrence of resonances. So to illustrate an inspiral, I will show you one of Steve Drasko's movies that he made, where he shows yeah, unfortunately, this doesn't really seem to. I'm sorry. Somehow it stopped working. Okay. Anyway, maybe I should restart the sharing. Okay. 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 Well, I'll just maybe. It's too bad. Anyway, so you should go to Steve Drasko's website and look at his movies. This is what an inspiral looks like, where the duration of the trace of the yellow line is 1 day. So occasionally you'll see it make these nice Lissajous figures. And that corresponds to commensurable frequency ratios. Yeah, well, at least you got some sense of what an inspiral looks like. Okay. Yeah, I highly recommend looking at these movies because they're really cool looking. Okay, so to describe an inspiral, as I said before, it is convenient to use action angle type variables to parameterize the orbit. So we have the angles Q alpha and the conserved quantities ELZ and Q for the actions J. So when you write the equations of motion that describe an inspiraling orbit in terms of these types of variables, they have the following form. The proper time derivatives of the angles are the frequencies plus small corrections, and the actions are conserved at leading order, but they slowly evolve due to self-force effects. So when epsilon is 0, these are just the geodesic equations in Kerr written in terms of the action angle variables. And the functions little and big g encode the effects of the self-forces. So there's a first order effect, and then there are also higher order self-force corrections. The key property of these functions is that they are 2 pi periodic in QR and Q theta, and they're independent of QT and Q phi because of the symmetries. So now I'm interested in finding approximate solutions to this system which describe the orbit approximately over an entire inspiral. So the simplest thing to try would be to just start from a geodesic and perturb off of that. But as I said before, this will quickly fail after the dephasing time, which is much shorter than the inspiral time.
Why are you showing one more order for decay?
Because this will be more, a piece of this will contribute to the motion at the same order as this will contribute. That's why I already showed it. Yeah, so therefore what we need is a formalism that allows us to have a leading order motion that is not a geodesic of the background. And a convenient method is the method of 2 timescale expansions, which work as follows. You simply write down an ansatz for the dependence on epsilon of the solutions that is a bit more complicated than just a straightforward power series expansion, and then you just justify this ansatz by substituting it into Einstein's equations and verifying it's self-consistent at each order in epsilon. So the initial ansatz will be based on adiabaticity, that the orbital timescale is much shorter than the radiation reaction timescale. This is a very good assumption for most of the inspiral, but it only fails near isolated regions in the phase space. So an example is the resonances, and then the other example is the transition from inspiral to plunge, where you have a separatrix crossing. But we can analyze these regions locally and obtain the non-analytic scalings with epsilon that arise, and then simply incorporate these into our ansatz to arrive at a composite expansion that remains valid throughout the entire inspiral. So in particular, I want to now introduce 2 sets of variables. One is a slow variable, tau tilde, defined to be epsilon times tau, and also a set of auxiliary phase variables, psi alpha, that are associated with the evolving frequencies. And the dependence on these psi alphas is assumed to be periodic. So we have a variable that captures a slow evolution, and then another set of variables that captures the periodicity. And these phase variables are defined by writing down an ansatz of this form that I've shown here. The thing to note is that the expansion starts at order 1 over epsilon in the phase. And this comes about because all of these expansion coefficients are just order 1 functions. But as I said before, the number of cycles of the inspiral scales as the inverse of the mass ratio, so 1 over epsilon. So this has to be reproduced in the ansatz for the expansion for the phase. And then we're going to treat the slow time and the phases as two different variables, two independent ones, and just write down the expansion for the solutions Q and J, where all the expansion coefficients are functions of these two variables. But I've already simplified the leading order ones. The reason there are these order square root of epsilon terms present is because there will be the transient resonances, and I've already incorporated them into the ansatz. I will explain this scaling in a minute. So at the leading order, the motion is a slowly evolving orbit, and given by these equations for the leading order coefficients, and the evolution is driven by the radiation reaction force on the conserved quantities, and in particular only the average over the two torus parameterized by QR and Q theta contributes to the adiabatic evolution. I'll denote this average by the angular brackets. So you'll note that this system is much simpler than integrating directly the equations of motion because epsilon doesn't enter. You can integrate these and take large time steps and a numerical integration and then restore the factor 1 over epsilon at the end.
Kind of adiabatic evolution that Steve
does. Yeah.
It's only averaging over GS, not over.
Yeah. So for most orbits that are non-resonant, this would be equivalent. So it is useful to also consider some more properties of the adiabatic approximation. And so because of the periodicity properties of the forcing functions, we can expand them in double Fourier series in QR and Q theta. So if I expand this forcing term G1, it has a 0, 0 piece, which is the piece that drives the adiabatic evolution. And then there are these fluctuating pieces where you can see that they have a fluctuating phase because the Q's locally in time are just the frequencies times time, though this just describes sinusoidal oscillations. So the torus average piece drives the adiabatic evolution, which describes a slow drift of the action variables. So here I show the action versus time. And then there are these small oscillations superimposed on this drift. And the amplitude of the oscillations is of order epsilon. So at the leading order, you can just use the approximation of the motion in terms of the overall drift. And then at higher order, you will have to take into account the oscillations and also higher order corrections to the drift rate. Yeah, and so we can systematically compute the higher order corrections. So to compute the phase correct to order 1, which is what is needed for gravitational wave data analysis purposes, we can write down equations of motion at that order, which I haven't shown here. But we find that they are written in terms of all the first order self-forces and a piece of the second order self-force, which is currently not known. So it is useful to look at what kinds of forcing functions are currently known to see what kinds of motions can be computed. So the first order dissipative self-force is known, and that's the torus average one, because, so the thing is, a formal expression for the self-force was computed over 10 years ago, but it is very difficult to implement that in practice because the self-force is formally divergent on the particle's location. So one has to use some sort of regularization scheme to deal with that divergence. But for computing the first order dissipative piece, one can use a radiative approximation that bypasses all of these challenges. So the dissipative piece is much easier to compute for the leading order self-force. So here the torus average piece is known. That is what, for example, Steve Drasko computes in his Tucholsky codes. Then the fluctuating dissipative piece is known in principle. It hasn't been computed yet, but it would be easy to modify existing Tucholsky codes to compute this piece. The conservative first order self-force is known for special cases such as orbits in Schwarzschild or equatorial orbits in Kerr. And there is currently much effort going on to compute it for generic orbits in Kerr. But this is more difficult to compute because it requires actually computing the local self-force and doing all the regularizations. The second order piece is currently fairly unknown. People haven't focused much effort on computing that actually in practice. But the second order piece will be needed at the same time as the first order conservative piece is also important. So this will give you the phase correct to order 1. But for generic orbits, there is a correction that dominates over these post-1 adiabatic corrections, and that is due to the transient resonances. So the resonances occur when the ratio of the polar to the radial frequency becomes a low order rational number. So omega theta divided by omega r is equal to k over n, with k and n small integers that have no common factors. During a resonance, the motion no longer fills out the entire surface of the torus, but instead is restricted to a one-dimensional curve. So I've illustrated this here where the upper panel shows the torus in phase space, and the lower panel shows the Boyer-Lindquist coordinates z and x. So for non-resonant orbits, the motion fills out the entire torus in qr and q theta space. And what you see down in the Boyer-Lindquist coordinates, so this is the z-axis for the black hole, here's the equatorial plane, and you have to imagine it rotated around to get the full picture, but you can see it goes all over this region. At resonance, then there's only the cycle on the torus, and in the Boyer-Lindquist coordinates, maybe you remember from the movie that there were these nice Lissajous figures that looked so appealing. During a resonance, the system no longer evolves on the radiation reaction timescale, but on a much faster timescale, which is intermediate between the radiation reaction and the orbital timescale. So the resonance timescale is T-res, which scales as 1 over the square root of epsilon times p, where p is the order of the resonance, equal to k plus n, where k and n were the frequency ratios that gave the resonance. So you can see how this comes about by looking at the expansion of the forcing function. For the conserved quantities, you have the 0-0 piece, which drives the adiabatic evolution, but then there's a Fourier harmonic that has a stationary phase at resonance, so it contributes to the average piece in order unity correction at resonance. But this contribution only lasts as long as the quadratic in tau piece is small compared to unity. Once this piece becomes of order unity, then the system is out of resonance, and that gives this scaling of the resonance time. So in principle, of course, there could be an infinite number of resonances, and corresponding to large integer ratios, but it turns out that only strong resonances have an effect on the motion. And strong resonances are those resonances where p is less than order log of epsilon, because the amplitude of these Fourier coefficients falls off exponentially with p. Those strong resonances, there are only a few of them, and we can treat them as isolated. So for orbits in Kerr, I've plotted here the frequency ratio versus the size of the orbit. So in the Newtonian limit to the right of the plot, the frequency ratio asymptotes to 1 because they're degenerate. But then it gradually ramps up, passes through a 3-to-2 resonance. Then there could be a few more resonances. And then I cut off the plot where it reaches the maximum of the radial frequency, because after that we have to switch to a near separatrix expansion anyway, so that is outside the scope of this talk. So the effect of a transient resonance is illustrated in this figure here, where I show the action versus tau. And you can see that long before the resonance, the adiabatic approximation given by this green slowly drifting line, is a good approximation to the motion. And after the resonance, the adiabatic approximation is again a good approximation. But during a resonance, there are order unity corrections that lead to a net jump in the mean value of the j's. So this jump can either be viewed as a jump to a different adiabatic solution, because in the absence of the resonance, the motion would have just continued on this lower gray shaded curve. Or you can think of it as a sudden change in the action without the corresponding time change that would have been predicted by the adiabatic approximation. These jumps scale as order square root of epsilon, and they affect the frequencies which depend on the actions. And this will give rise to phase errors of order 1 over the square root of epsilon after further inspiral. So this becomes 1 over square root of epsilon because the phase has this factor 1 over epsilon for the number of cycles. So it gets enhanced because epsilon in principle is small, so 1 over square root of epsilon could potentially be large. We can also compute the jump analytically by performing a local analysis in the resonance zone, where the dynamics are one-dimensional in the resonant phase combination Q, which is KQR minus NQ theta. And we can use matched asymptotic expansions to compute an expression for the jump, which depends on the various forcing functions, G00 and the resonant forcing piece, and derivatives of the frequency, and most importantly, it depends on the phase entering the resonance to order 1. And remember, order 1 for the phase means it's a higher order correction. And it is quite important to get the phase correct to order 1, because here I've shown you the effect of differences in the initial conditions before and after the resonance. So here I show again J versus tau, and there's a resonance region here. So if I change the phase at order 1 before the resonance, it just makes a small difference of order epsilon between the different J's. But then once it encounters the resonance, this gets magnified to become of order square root of epsilon differences. So for the actions, this is of course still small, but in the phase again, it becomes 1 over square root of epsilon. So it is quite important to know the phase accurately to order unity. And in case there is a subsequent resonance, we also need to compute higher order jumps in order to have the phase after the resonance correct to order unity. The resonances have several interesting properties. There are non-perturbative effects in V over C and are not seen for analogous post-Newtonian systems in the weak field limit. They occur for fully generic orbits that are both eccentric and inclined, and they have to be around spinning black holes. They don't occur for Schwarzschild orbits. They're driven by the fluctuating dissipative piece of the self-force, and in particular only the piece that depends on the black hole's spin. They also cause increased sensitivity to initial conditions, not chaotic, but in the sense that I've illustrated here. When you look at the phasing and you look at the various approximations that you can use for it, with the adiabatic approximation on top, and then various higher order corrections down below, then you can see at resonance, information flows from a higher order to a lower order in the perturbation expansion. So this is the sense in which it becomes more sensitive to initial conditions. So because this 1 over square root of epsilon for the phase could potentially be large, for small mass ratios, we wanted to get an estimate of the net size of the phase error that comes about for extreme mass ratio inspirals. So we integrated the Kerr geodesic equations supplemented with post-Newtonian forcing terms. And what is different than the usual ways of computing inspirals is that we use the instantaneous forcing terms, not the orbit averaged ones. So in the upper panel here shows the correction to the conserved quantities scaled to their values at resonance, and also with the square root of epsilon scaled out. And the x-axis is the size of the orbit in both panels. The lower panel is for the phase error in number of cycles. So here the system passes through a 3-to-2 resonance, and you can clearly see the kick in the conserved quantities, and correspondingly in the phase, the red downward trend in the phasing error, which results in about 15 cycles of phase error due to the resonances. And for comparison, we also showed the phase error due to the first order conservative self-force, which is a post-180 adiabatic correction. It should give phase errors of order unity, and indeed it is only a few cycles. So, in summary, transient resonances are a qualitatively new feature of the relativistic two-body problem. They occur for fully generic orbits, make the orbit more sensitive to changes in the initial data, and they give rise to phase corrections that scale as the inverse of the mass ratio square root, and are characterized by sudden jumps in the time derivatives of the phases. Computing these corrections will require currently unknown pieces of the gravitational self-force, and numerical estimates indicate that the phase errors are of order 10 cycles for mass ratios of order 10 to the minus 6. But of course, with the caveat that we have to use post-Newtonian self-forces to make these estimates. And we're currently pursuing several further investigations of this.